Till now, we have been dealing with straight lines which are parallel to a plane or perpendicular to a plane. That is, they are independent of the plane in general. What if we have a straight line which is lying on a given plane? That is, we know the equation of the line completely as well as the equation of the plane, and also the geometrical condition that the line completely lies on the plane, instead of the earlier versions where the line were intersecting the plane at one point or were parallel to the plane or something like that. What if a line in 3D space and in the standard equation of a line in three-dimensional space is lying completely on a given plane? Let's look at the conditions for such an event to occur. If the line r bar, we are of course looking at the vector form first. If the line r bar equals a bar plus lambda b bar lies on the plane r bar dot n bar is equal to d. Remember, d is the shortest distance between the plane and the origin. N bar is the vector normal to the plane. Then b bar dot n bar is equal to 0 and a bar dot n bar is equal to d. In the Cartesian form, if the equation of the line is x minus x1 by L equals y minus y1 by m equals z minus z1 by n, and it lies on the plane ax plus by plus cz plus d is equal to 0, then ax1 plus by1 plus cz1 plus d is equal to 0 and al plus bm plus cn is equal to 0. Both these conditions are obtained from the vector conditions for the line to lie on the plane. And thus we have these two Cartesian and vector forms. So please remember, why is this? R bar dot n bar is equal to d, being the plane that contains the line r bar is equal to a bar plus lambda b bar. B bar dot n bar is equal to 0 is obtained because the line is parallel to another vector b bar. Okay, and since n bar is a vector which is normal to the plane, n bar is going to be perpendicular to every line which is lying on the plane, and therefore the dot product of n bar with any line on the plane is going to be equal to 0, and thus b bar dot n bar is equal to 0. Moreover, a bar dot n bar of course represents the shortest distance between the plane and the origin. Therefore we get this condition, a bar dot n bar is equal to d, and converting it into the vector form, we get ax1 plus by1 plus cz1 plus d is equal to 0 and al plus bm plus cn is equal to 0, where x minus x1 by L equals y minus y1 by m equals z minus z1 by n is the equation of the line, and ax plus by plus cz plus d is equal to 0 is the equation of the plane. Remember, a, b and c in this equation of the plane represent the direction ratios of the normal to the plane.